In this video, I want to give you an overview of how you can use AFL++ to fuzz test a program. Whether it's your own code or you're doing security research, this is a great skill to have. So let me show you how to do it by telling you my story of me trying to fuzz libwebp in an attempt to rediscover the crazy vulnerability that was used to remotely hack iPhones with a malicious webp image. This video is sponsored by our training platform hackstreet.io, more on that later. I'm not super experienced with fuzzing, but I want to learn. And so in early October I was working on a different fuzzing experiment involving sudo and pkexec. Both are well-known Linux tools with seemingly easy to discover vulnerabilities. I was trying to create a naive fuzzing setup to rediscover both. About sudo, I actually made an in-depth, very technical series going from discovery up to developing the exploit. So go check that one out, but not that important. Important was that I was hanging out on the awesome fuzzing Discord. And at that time, this message showed up from Van Hauser. I was able to find the libwebp 0 day twice with AFL++ with 1 instance comconf and 5 normal instances running for 2 days. And at that moment, I immediately dropped everything. The libwebp vulnerability is really crazy because libwebp gets fuzzed by OSS-fuzz, continuous fuzzing for open source software. It's basically a massive fuzzing server farm by Google, fuzzing lots of different open source projects, and it found over 10,000 vulnerabilities. So when you are fuzzing something as prominent as libwebp, then you have to compete against OSS-fuzz. So the fact that Van Hauser was apparently able to find the bug in 2 days tells me that he must have had a very unique and interesting approach. And by trying to replicate his method, I thought it's a great chance for me to learn more advanced AFL++ workflows. I think learning has to be a balance between somebody telling you information but also discovering things yourself. This has always been true for me, so I did not just want to copy and paste Van Hauser's setup, instead I wanted to start mostly trying it myself. And when I realize I get stuck or don't see results, I can always ask for more and copy from him. But then I also try to figure out, why did he do this or that? Did I know about this or not? And so forth. And so I went ahead and based on this small amount of information, I tried to set up fuzzing myself. Now let me walk you through the process of a basic fuzzing setup with AFL++. By the way, if you want to understand the basics of AFL in general, how coverage guided fuzzing works, check out episode 2 of the sudo series, how fuzzing with AFL works. But now let's get started. We want to fuzz libwebp, and as the name indicates, it's a library. It's intended to be included into your own project. That's why it's used in Chrome or even iOS. It's not a standalone program. This means we need some kind of harness, an example application that will call into the library so we can fuzz it through that. But generally you don't have to write that yourself because usually these libraries come with example programs. And look, there is an example folder as well, which if you look through it, you can find here dwebp.c, command line tool for decoding a webp image. So if we compile and instrument libwebp and this example binary, we can fuzz it. So now that we have a rough plan, the next step is getting familiar with the target by following the basic setup instructions. Compile it and check if the dwebp example does what you think it does. In our case, for fuzzing with AFL, we want it to ideally take a file name of a webp file to parse and decode it. That's what AFL will work best with. And looks like it does the job. Passing in a file, it shows us some details about it. Next, we can basically follow the AFL instructions. We have to install the dependencies and then compile our target with the coverage instrumentation by AFL. To do that, instead of using GCC to compile your program, you would use AFL GCC, which is a drop-in replacement for GCC. Or rather something more modern like AFL Clang Fast or so. But the problem is, in larger C programs, you don't really call GCC yourself. There are makefiles and oftentimes a configure step. Though typically you can specify the compiler with the cc and cxx environment variables. So in the AFL README, you can see that before calling make to build the project, try to change the compiler by calling configure with the cc environment vars. If that doesn't work, you can also try to modify the makefile by hand and change the compiler that is used. But for libp, using the environment variables works nicely. And now let me show you how I set this up. I like to prepare a Docker file and generally do the fuzzing in a container because I like to develop it on my local machine. I don't clutter my system and I can easily move it over to a better server later. So I first create a base image using Ubuntu where I then install all the tools, GCC, Clang and LVM to compile stuff, wget and git to download stuff, and all the other dependencies needed for AFL++ or libwebp and whatever else I might need like Vim or Python. Next, I clone AFL++ and install that. And because I only plan to fuzz webp, I'm also grabbing libwebp and check out the vulnerable version. Next, let's build the container with docker build, and then let's run it with docker run. I also mount in the current working directory as a shared folder into pwd, and we also have to run the container in privileged mode calling ptrace and so forth. And then we can use docker exec to get a shell in the container. By the way, if you want to learn more about Docker, I also have videos where I explain it in depth. Anyway, everything else now I do in a script, but I don't write the whole thing down in one go. I do this step by step by hand, keep the container running and modify the script and iteratively build up this whole thing. So the script is more like me taking notes along the way. I always test and run into issues and then adjust the script. The result you can see here. It's pretty basic. You can see I basically follow the libwebp instructions, and at the configure step I set the AFL compiler. After building libwebp with make clean all, I then copy the whole directory with the compiled binaries and libraries to their own folder. Now, theoretically, we would be ready to start fuzzing. But if you read the fuzzing in depth documentation from AFL, it would also tell you to seriously fuzz, you should use multiple CPU cores by starting multiple fuzzer instances. You should have one main fuzzer indicated by -m and then multiple secondary fuzzers with -s. And not only that, there are different instrumentation and coverage strategies mentioned here. For every secondary fuzzer, there should be a variation. By the way, Van Hauser also mentioned this in his original message. Most important is probably an address sanitizer build because it will detect buffer overflows. But they also recommend cmplog and comconf. I don't really know the details of the different instrumentation, so let's do a quick experiment. I asked ChatGPT to write a shitty program, and then I compile it with the different version, as you can see here, and then I look at them with Binary Ninja. So what you see here is a graph view of the parse, JSON, and find key function. It's not quite assembly, as you can see. It's Binary Ninja's HLIL representation, which is nicer to read than just assembly. Anyway, this is the function when you just compile it in GCC. There's a string stored in var 18, and then later it's passed to the function isMatchingKey, and that then has a loop to loop over the input string LiveOverflow to see if that matches. Pretty clean translation from C code to assembly. But now let's look at the AFL instrumented binary. Here you can see that the function became massive. That has two reasons. First of all, when you look more closely, you see these pointers to the AFL area. This is a memory area where basically, depending on the path that is executed, it will set different bits. And that's how AFL can check the coverage. More bits set, more code reached, different bits set, different code paths reached. So this is now included everywhere in every thinkable step. The second reason for this function to be so large is that the LiveOverflow string compare loop was apparently unrolled into individual steps. As you can see here, it goes character by character. This is pretty clever for a fuzzer with randomly mutating data. It would be quite hard to guess the whole string LiveOverflow randomly. Unrolling the loop, going step by step, allows the fuzzer, through increased coverage, to basically brute force the string character by character. If we now look at the binary with cmplog compiled, we can already see that the function is not unrolled again, and we just pass a string to isMatchingKey instead. But besides the AFL area pointer, we also now have an AFL compare map. So again, another strategy to collect coverage. And lastly, comconf. Here the graph of the function looks different again. It's also unrolled the loop, but visually you can see that the blocks are different. So I guess different strategies of collecting coverage again. Anyway, long story short, AFL has different strategies to calculate coverage, and to be honest, I don't really understand the difference for real, but we saw the difference, and by using all of them in parallel, your fuzzing might be able to find more. So I compile an ASAN, comconf and cmplog version as explained in the AFL README and copy them into unique locations. Now we are almost ready. We just have to get some initial files first. So I just downloaded a bunch of test.webp files. In the signal source code, I found a few different ones and placed them into the tmp in folder. And now we can start fuzzing. I use screen to start multiple instances of AFL Fuzz in the background, one main instance and then multiple secondary instances. I specify the in folder and the out folder, and because I got some errors about the library path, I'm also using AFL target env to set the LD library path environment variable to the correct folder for that binary. And the binary that we are fuzzing, well, that is dwebp located in the respective folders. With add, we then tell AFL where to place the input file for fuzzing. And that's it. We start the fuzzing campaign. Now we can check that all screens are running and that looks good. And now we can attach to the screens and see their progress. And now we just have to wait. 12 hours go by, still no crash, but 1000 said 2 days, so let's wait. After 2 days, still no result. And so I go back to Discord. I'm at 2 days now, so far no finding. Rich in Seattle pointed something out I had completely missed in the original message. The trick why it should work. Van Hauser wrote, I made a little trick though. I had an example crash input, so I ran that with coverage, obtained the function names and only instrumented those functions with the environment variable AFL LVM allow list. So when I read that, I was thinking, okay, this is probably clever because you already help guide AFL to the functions you are actually interested in, and you don't waste time exploring coverage in other areas. Maybe that's the difference to OSS Fuzz. And a few days after that one message, he also published his blog post, Advanced Fuzzing, Unmasking Elusive Vulnerabilities, where he shares all the setup details, including the LLVM allow list that he used. But I was thinking that with this list of functions to focus on, fuzzing would just be faster in finding the overflow. And so I thought I can just run my fuzzer longer with the complete function coverage. And it would be interesting to see the difference in time it takes. His takes 2 days versus my... Let's see. But as mentioned before, libwebp had been fuzzed extensively already. So maybe some other small detail was responsible for his success. And so I wanted to compare my setup with his and adapt some of his methods. In this process, I can also see the gap of my knowledge versus his, and I can learn. So first I noticed that I hadn't really used CMP log correctly. I used -m none from the README while he didn't do that and instead uses -l2a and -l3at, which is some crazy stuff I don't understand, but whatever. There's one other thing though I noticed, and that is that he added AFL init into main, which I think is just a speed up because no need to fuzz anything before main. But now with those changes I felt confident. I thought now I replicated everything except the function allow list. So let's try again and see if we can find it over time. And time passes. I'm busy with other projects, with other work, and busy working on Hextree. If you like this video and you want to learn more about hacking, please check out hextree.io. This is an online training platform developed by Stack Smashing and me, and we try to create the best video tutorials to learn hacking. It's a lot of work and we are not fully public yet, but we are eventually getting there. So I would appreciate it if you check out hextree.io. Around mid-November, I think, so like 1 month later, I started to get suspicious. I had no results yet and I decided to fully copy Van Hauser's technique. I decided to also set the allow list. With that, I started to fuzz in parallel and expected to find the crash in 2 or maybe 3 days. I actually tried 2 different versions, just adjusting a little bit the secondary fuzzers, and one ran for 12 days and the other one for 7 days. But no crashes. Let's think. What is the only thing that makes my setup and his setup different? Either it's a grave mistake in my setup, which is very likely by the way, or it's his input corpus. Maybe he just had much better initial test images that reached deeper and were closer to the crash. So I decided to go back to the Discord and ask him to share his test image. I typed into the search webp to find his profile, and then there was this message. I sadly have to report that somehow a corrupted webp file I experimented with in parallel got into my fuzzing campaign when looking for the webp vulnerability. I restarted the fuzzing and trying if my setup is able to find the bug without my fup. It will take 1 to 2 days. I will update the article then accordingly. And well, 3 days later he reports the article is updated. By the way, it's early December now and he sent these messages in October. I spent the whole October and November fuzzing and I missed this message saying that it was an error. Oh man, I was so happy to read this. Oh my god, I thought it was so crazy that he found this bug in a fairly naive fuzzing setup that OSS Fuzz didn't find, but it just ended up being a mistake. And I'm very glad about that fact, because that proves again that this vulnerability could not have been found through this naive fuzzing approach. As Van Hauser writes in his blog post, this libwebp vulnerability is an important reminder to understand that fuzzing is no silver bullet. Some bugs are impossible to find with fuzzing. To this day, I haven't given up though. My original fuzzer is still running over 100 days and counting, and it still says in progress, and 11 days ago it found some new coverage. So you are telling me there's a chance? Okay, this approach failed. But I hope seeing the general setup helps you to create your own fuzzing campaign for a different project. And thanks to Van Hauser, we also learned about quite some advanced tricks and techniques for AFL. So please also check out his article, it's really helpful. But now let's actually go deeper into WebP and let's try out a different mode of fuzzing. If you remember from the first video, the vulnerability was in the build Huffman table function. This is the function implementing the Huffman table logic with the buffer overflow. So let's try to fuzz build Huffman table directly using AFL Persistent Mode. In Persistent Mode, AFL++ fuzzes a target multiple times in a single fork process instead of forking a new process for each fuzz execution. This is the most effective way to fuzz, as speed can easily be 10 times or 20 times faster without any disadvantages. All professional fuzzing uses this method. And here in the README you can see an example for a fuzztarget.c. You have to call AFL fuzz init, then here is main, and in main you need two important values. First of all, you get a buffer where AFL will place a pointer to the test case. So this is the fuzzing input data. And after that comes a fuzzing loop, and inside that loop you get the length of the test case. And now with this length and the buffer pointer, you somehow prepare your target function and call it. So let's adapt this to fuzzing the build Huffman table function. As you can see, I built up the program in the same way. We have fuzz init, main, we get the test case buffer, the fuzz loop and the length, but then comes a bit more logic, because we now have to prepare the parameters for the function wp8l build Huffman table. You can find this function in libwebp and huffmanutils.c, and it takes a root table, root bits, code length arrays, and the code length size. As you can probably guess, setting this up gets a bit more complex. Now you really have to read some code and really understand what the parameters mean and how you can prepare them. I don't want to go into too much detail. We already briefly looked at the code in the last video. As you know, there are multiple tables. So let's just try to fuzz the table that has 40 symbols, which according to enough.c requires a max table size of 410 entries. So I define the values here. The 40 is also the code length size, because this array stores the code lengths for each symbol. We have 40 symbols, so 40 entries. And these entries are actually the important fuzzing input, so we now use the buffer to set the values of the array. We loop through it and pick one byte from the buffer, modulo a max value of 19, that's the maximum code length, and now we basically generate a random code length array with the AFL fuzzing input. Below that I also created the corresponding count array. You might also remember this from the last video. It's actually created inside the build Huffman table function. I just added it here as a debug output because that's the array everybody talks about, and so I wanted to print it. Anyway, two parameters of the target function are still missing, though root bits, it's actually constant, we know it's 8, and the last thing missing is the table. That's the table buffer we overflow. This table is an array of Huffman codes, and we know it should be 410 large. And now we can call the function and we basically are ready for fuzzing. By the way, this program is intended to be placed inside the libwebp source code, so we can include the real huffmanutils.c and then directly call the function. It works well here, but if you cannot get this to work in your case, you could also copy the code from the target into your C file and define all the missing types and functions. You just somehow have to call the target code, whether it's through including the original files or copy everything into one C file. Anyway, I prepare a Docker file again with the dependencies like before, and I create a new fuzz script. Remember, in this case, we are fuzzing a function directly. So the input data in this case is the code length array, not an actual full WebP file. so I just generate some random files as input. Then I copy the fuzz test Z program into the libwebp source folder and create a non-AFL version for printing the count array. But more important, here's the AFL instrumented version and an address sanitizer version. And then, like before, we start the screens with AFL fuzz. So here we go. We start fuzzing and we wait. Or do we wait? As you can see, the regular build does not find a crash, but look at the speed, 6,000 to 7,000 executions per second. Compare that number to the fuzzing of the complete binary from before. But that's not all. Look at the ASAN build. In under 1 minute, we crashed thousands of times. Did we just discover the vulnerability? Using the non-instrumented binary, we verified that. Let's take one crash test file, cut the file into the non-AFL binary, and we get the count array. I've created another tool called count to size, which tells us how large the table would be, and it turns out it's 414 entries large. 4 bytes larger than the table is supposed to be. We can also now increase the table size in our fuzzing program, for example, to 500, and we compile everything again and fuzz again. It takes a little bit longer, but we also find a crash in under a minute. This time we managed to find a count array that results in a table of size 520. Isn't that crazy? Fuzzing the build Huffman table function directly. If you would know exactly the table size and the parameters, the fuzzer, just like that, has no problem to find a crash. So let's briefly talk about the problem. Why did regular fuzzing not find it? The problem, I think, is in this case is really that the table buffer is shared between all Huffman tables. If we go back up the call stack, we end up at the call read Huffman code where the table is passed in, and unfortunately the size of the table is not super clear because here it's allocated. And Huffman table is a pointer into that buffer, and then the code loops over all trees and moves the pointer in the table forward. And that's why triggering the overflow was so difficult. The first 4 tables had to be basically filled up to almost their max size, but not larger because, yes, they theoretically overflow their allocated part, but that is safe because they operate on the combined table buffer, which is huge. So no overflow yet. And if they are too large, then they eventually error out. So the first 2 tables had to be basically at max size, and then only the last one had to overflow. And the problem is, as you have seen with how coverage gathering of AFL works, the function build Huffman code gets great coverage already by the first table and the second table. The way the code is structured, I think, is just very, very bad for fuzzing and bad to read, to be honest. And maybe that's the lesson here. If you are a developer, try to write code that is easy to fuzz. I know it seems like redundant code, but if there were maybe 5 different functions handling each table separately instead of a combined buffer and a loop, I believe fuzzing the code would have found it through the coverage. Maybe that's something somebody could test maybe. And for security researchers, the lesson is fuzzing is awesome, you just have to deploy it precisely. By the way, all my code for reference is on GitHub if you want to check that out, and let me know if you tried regular AFL fuzzing or persistent fuzzing on a project of your own. I hope you found this interesting, but there's still one big question. If fuzzing couldn't find it, and we only found it with persistent fuzzing because we knew where to look, how did they discover this vulnerability in the first place? I actually have a theory, and I will tell you all about it next video. If you like this video and you want to learn more about hacking, please check out hackstreet.io. And if you would like to support LiveOverflow videos directly, check out my font at shop.liveoverflow.com. It's definitely a shitty present to yourself or people you hate. And besides that, maybe also consider becoming a Patreon or YouTube member. Their financial support is very appreciated. Thanks and see you soon.